Cyprian. I'd like to first thank the organizers for putting together this wonderful school, and it's a great pleasure to be here. So today I'm going to talk about the physics of fractionalized electrons in systems with barrier phase. So this work is really driven by my former group members and current and former group members. So Valentin Krappel and Mishaga, former students, and Trithab, Yang, and Hart Goldman, former postdocs, and they have all moved on to new faculty and postdoc positions. And then the recent work is done with my current group members, Aidan, Reddy, and Hugo, PhD students, and Ahmed is a postdoc. And we also had a lot of collaborations with experimentalists working on fractionalized quantum Mom's Hall fractional training tutors, Xiaodong Xu from UW, Ben Feldman at Stanford, and my colleague Long Zhu and Zheng Guanglu before he moved here. So I'm sure you've heard a lot about the fractional quantum Hall effect already, but let me just briefly remind you. So first, quantum system that shows fractionalized excitations are quantum Hall systems. These are two-dimensional electron systems under a strong out-of-plane magnetic field. And in these systems, even though it's made of electrons, you get quasi-particles that carry fractional charge, and they obey fractional quantum statistics. And for many years, this has been the only system where quantum fractionalization has been demonstrated experimentally. And a lot of the beautiful work on the fractionalized quantum Hall effect was done here in Tallahassee, and they all require a strong magnetic field. But the physics really is universal, and you take essentially any high mobility semiconductors, such as gallium arsenide, silicon, zinc oxide, or with the advent of 2D materials in the 21st century, graphene, two-dimensional semiconductors, WSE2, and et cetera, all these high mobility semiconductors under a strong magnetic field fractional quantum Hall states. Okay. Now, starting from just 2 years ago, a new type of fractional phases has been observed, and now these are so far has been observed only in two materials. These are moire materials made of van der Waals heterostructures of 2D materials. And they show a lot of similarities in terms of phenomena with the fractional quantum Hall effect, but it all happens at a zero magnetic field. And that is the physics I want to discuss today. Now, before I go on, maybe one question that's on the back of your mind is, do we still need MagLab, right? This fractionalization occurs at zero field. We still need it? Okay, the message of my talk is that, yes, we actually need a stronger magnetic field. Towards the end of the talk, I'll tell you why. In fact, we need a 200 Tesla field to, I think, fully reveal the physics in these moire materials. Okay, so what's special about magnetic field, right? Historically, it's actually quite interesting. From the point of view of classical mechanics, we know that for particles, charged particles moving on the magnetic field with velocity v, it experiences a Lorentz force. It's always perpendicular to the velocity. Now, on the other hand, if you think about classical statistical mechanics, the partition function, which determines free energy, determines all the thermodynamic properties of the system, is actually independent of the magnetic field. And this is because when we integrate over the phase space of a particle's position and the momentum, the way the magnetic field enters is that it comes through this minimum coupling. It's momentum P couples to the vector potential A, but one can actually shift the momentum to eliminate this vector potential, and therefore it has no effect. In fact, historically, Maxwell wrote in his treatise on electromagnetism, explicitly stated that there should be no effect of magnetic field on electrons in conductors. But then Hall did this experiment, and he found what is now known as the Hall effect, that if you have a pass current through a conductor in the perpendicular magnetic field, there's a transverse voltage. So there's a Hall resistance. And the Hall resistance is what you expect from the Lorentz force. Basically, the balance between the Lorentz force and the transverse voltage keeps electrons moving straight. Right? So one has to balance the Lorentz force, which is proportional to V times B, with the transverse voltage. And from that, you find that the rho xy is linearly proportional to magnetic field and inversely proportional to particle density. Okay, so really, to understand what magnetic field does to charged particles, one need quantum mechanics. So in a quantum theory, a vector potential cannot simply be eliminated by a momentum shift because in the magnetic field, charged particles undergoing cyclone motion, and in order for the wave function to be single-valued, then it's not possible to completely remove the vector potential. And in fact, as a particle moves around a closed loop, it's known to pick up a phase factor that's called a Harmon-Born phase, and this form factor is exactly the line integral of the vector potential, which is by Stokes' theorem is equal to the magnetic flux enclosed in this area. So this quantization condition determines the energy of electrons in the magnetic field. So instead of being a continuous spectrum, it now quantizes into discrete levels known as lambda levels. And each quantized orbital occupies an area that corresponds to exactly one flux quantum. So a Harmon-Born effect is crucial for understanding charged particles in the magnetic field. So in a high magnetic field, was found that when the integer number of lambda levels are occupied, an energy gap develops, and in this case, the system shows a quantized Hall connectivity. Basically, an integer fitting factor sets the density of electrons to be an integer multiple of the lambda level degeneracy, which is proportional to B, and then you plug into this classical formula, you immediately get quantized value. Okay? So really, the quantization of the Hall effect in the magnetic field all has to do with the presence of energy gap. So at a certain fitting factors, as when energy gaps develops, the Hall conductance will be correspondingly quantized. The Hall connectivity is always the fitting factor times E squared over H. And at integer fitting, the system develops an energy gap because of the single particle energy spectrum shows cyclone gap. But then, and the in higher magnetic field, when we enter the fractional fitting regime, when the number of electrons is less than the lambda level degeneracy in the lowest lambda level, and in this case, single particle physics will predict a huge ground state degeneracy. There's massive degeneracy, but interactions lift this degeneracy, and out of the interaction in the partially filled lambda level emerges a strongly correlated quantum liquid, known as the fractional quantum Hall liquids, and they occur at a sequence of fitting factors Q over Q. And again, I won't go into the details, but as soon as these many-body gaps develop, we get incompressible quantum liquids. There will be a corresponding quantization of the Hall connectivity, but now it's a fractional value, such as 1/3. Again, I'm sure you've heard this already in the previous lectures. One way to understand this is to take the composite fermion picture. You attach, for example, 2 flux to every electron to convert into the composite fermions. And after this flux attachment, composite fermions sees a different magnetic field, typically reduced from the original field, reduced by this amount that's tied to the density and the multiplied by the 2 flux quantum, okay, for each electron. And then again, to understand the fractional quantum Hall effect at a fitting factor P over Q, then one can think in terms of these composite fermions. Now they experience a different magnetic field. They'll have a different fitting factor. And so when composite fermions occupy an integer set of the corresponding lambda levels, then similar to the integer quantum Hall effect for electrons, the composite fermions system will develop a gap. And now this occurs at a different electron fitting factor, which is P over 2P plus minus 1. And this explains a whole sequence of fractional quantum Hall liquids known as the Jane sequence. Now, regardless of the microscopic origin of the fractional quantum Hall states, there's a important, a beautiful argument due to Laughlin, and he pointed out that as soon as quantum Hall effect, Hall conductance is fractionally quantized, the system necessarily hosts fractional charges. And the Laughlin argument goes as follows. Suppose, imagine we thread a flux quanta through a thin solenoid, and we turn on the flux of the solenoid from 0 into 1 flux quanta. And this time-dependent flux then generates a circulating electric field in the circumferential direction. And because of the quantized Hall response, this circumferential electric field then drives current in the radial direction. So at the end of this process, as the flux quanta increases from 0 to 1 flux quanta, the total charge that has been pumped across the entire sample is then equal to the integral of sigma xy times d phi dt, and this becomes sigma xy times h over e if the flux changes by 1 flux quanta. So if the Hall conductance is, for example, 1/3, then this immediately says that after this flux pumping, we get a minus 1/3 fractional charge at the origin and a plus 1/3 charge at the boundary of the sample. So why 1 flux quanta is important is because after threading 1 flux quanta, one can perform a gauge transformation. So the system with and without 1 flux quanta has the same energy spectrum. So this means that at the end of this process, the fractional charge that's been created in the system is a true excitation of the system without any flux, any additional flux. Okay, so this is a very general argument showing that fractional charge and the quantization of the Hall effect, the fractional quantization of the Hall effect, essentially go hand in hand. Okay. So in a broader context, back in the 1980s, before I was born, it has been pointed out that by David Thales and Tian Yu and Yongshi Wu that the quantization of the Hall effect actually has a deeper origin. Okay, it's deeper origin. It's actually a topological invariant of the system. So whenever the Fermi level lies in the gap, the bulk Hall conductance can be written as a topological invariant, and this applies to integer quantum Hall effect as well as fractional quantum Hall effect. Okay, so really the quantization of the Hall effect has a topological origin that's tied to the many-body wave function of the system. And Haldane pointed out that in addition, instead of applying a magnetic field to create a quantum Hall effect, integer quantum Hall effect using lambda levels, one can consider toy models, and a model for an insulator with an energy gap between conduction and the valence band. But under the right condition, the valence band can have a non-zero topological so-called Chen number. And in this case, when the Fermi energy lies within the single particle band gap, the system would show a quantized Hall effect with an integer Hall conductivity determined by this integer Chen number. So this is an example, an early example showing that a band with a Chen number, a Chen band, can play a role similar to lambda levels to give rise to quantum Hall effect. Okay. And for a long time, this has been a theoretical dream, but with the discovery of topological insulators, this became a reality. We know that topological insulators carry Dirac surface states. The Dirac cone has a twofold degeneracy associated with electron spin protected by time reversal symmetry. And we pointed out early on that if you apply a Zeeman field to break the spin degeneracy, and in this case, then the surface state actually carries 1/2 Hall conductance, with one half of Chen number, and then combining the top and the bottom surfaces, if they have developed the Zeeman gap of the same sign, then the total Hall conductance will be 1/2 plus 1/2. It will be the integer multiple of d squared over h. And the experiments from Qi Kun Xue's group in Tsinghua University in 2013 indeed observed this quantized Hall effect at zero external magnetic field. And the Zeeman gap on the surface is introduced by magnetic doping. So this is the thin film of topology insular with magnetic dopants throughout the system, both on top and bottom surface. Now, in this system, you may ask, once we have this Chen band, can we imagine fractional fitting of the Chen band to realize a fractional, the analog of fractional quantum Hall effect? And this system, there's no chance, because each band here hosts a very high density of electrons. Okay, these are the systems with an atomic scale unit cell, and the density that corresponds to 1/3 or 2/3 fitting of this band is extremely high. There's no way to use electrostatic gating to achieve this regime. And also in this system, the Chen band is very dispersive. It has large band widths, and it's not at all flat. Okay. So, throughout the decades, theorists have asked this question: can one achieve the fractional quantum Hall effect without magnetic field? And one of the early example is the chiral spin liquid state proposed by Laughlin. And here you can view a spin 1/2 degree of freedom as a hardcore boson. Spin down is no boson, spin up is having a boson. So then a half field lattice model of spins, a lattice model of spins can be viewed as a half filling of hardcore bosons. And Laughlin and collaborators envision a fractional quantum Hall state of bosons on the lattice. And since then, there has been many works, for example, in cold atom systems, using a rotation and create a analog of a magnetic field. But then I think in the quantum materials community, activity really exploded since 2011. It was many theorists envisioning that you take a Chen band, right? But now, suppose the Chen band is very flat, then this can become similar to lambda levels. It can drive the fractional quantum Hall effect. And there have been many toy models on the lattice that demonstrate numerically this indeed occurs. And my interest in this subject is really motivated by the analogy. Okay, so the question is, we really want to find an analog of magnetic field in quantum materials. Okay, as I mentioned, the fundamental level, the real effect of magnetic field is to produce an Harman bond phase for a charged particle. And we know there's another way, okay, to create a non-trivial phase vector, and that is so-called the Barry phase. So consider a particle moving in a spatially varying environment, and suppose the internal quantum state of this particle, for example, a spin of the particle, is spatially varying. And then when this particle moves around a closed path, it will pick up a Barry phase that is precisely take this form. And it has a 1-to-1 correspondence with a Harman bond phase, except now the vector potential is replaced by the spatial variation of the quantum wave function of this particle. Okay, and so this is a way a material with a spatially varying internal quantum texture, it can generate an emergent magnetic field. And the message of my talk is that this emergent magnetic field is as real as real magnetic field. It can drive a whole set of phenomena. Okay. Now, this idea has been conceived quite some time ago, and in particular, the framework I'm going to be using is considered a particle in the continuum space with kinetic energy p²/2m, and this particle has a spin degree of freedom, which I call a sigma. Okay, it's a spin 1/2 particle, and it moves in the background of a Zeeman field, and S of R is the classical background Zeeman field. It varies spatially. Okay, in particular, the orientation of the Zeeman field is spatially varying. Okay, so this is the Hamiltonian I'm going to start with. Now, when this exchange coupling J is very large, the particle's spin is locally locked to the background Zeeman field. And in this case, it's useful to do a unitary rotation, a spatial dependent unitary rotation that rotate the electron spin into the local Zeeman axis. So this exact transformation, after this exact transformation, one can derive a new Hamiltonian that is completely equivalent to the original one with the same energy spectrum. And then this new Hamiltonian is a 2x2 matrix in spin space, but now the diagonal term is all in the local Z basis. So in particular, we're going to focus on the first block H1, where the quantum particle spin is aligned with the local Zeeman field, and H2 is a high energy subspace where the quantum particle spin is anti-parallel to the local Zeeman field. And then there are off-diagonal terms connecting low and high energy subspace. Okay. Now, if you carry out this calculation, simple calculation, you find that in the diagonal block, now particles do not have the spin has been frozen, the spin has been locked to the Zeeman field, but now a new gauge field appears. In particular, in the diagonal part of the Hamiltonian, there's a U1 gauge field that appears, and the off-diagonal part, it involves the off-diagonal component of the gauge field. This gauge field little a is an SU2 gauge field. Now, when the coupling is very strong, okay, all the low-energy degree of freedom lives in the upper block, H1. So in this case, we can neglect all the other parts of the Hamiltonian, and we arrive basically at a theory of a effectively spinless particle, but now moving in a gauge field and in a gauge potential. So the corresponding gauge magnetic field, the curl of A, is exactly given by the Berry curvature, given by the spin chirality, while the scalar potential is exactly given by the gradient of the spin, okay, which in a general setting is quantum metric. So one thing I want to emphasize is that the emergent magnetic field is to first order in the H bar, okay, is a leading order quantum correction, and the scalar potential is proportional to H bar squared. It's second order, okay? So these two effects, they appear naturally in a system of particles coupled to a spatially varying Zeeman field. Now, and I should mention that this was studied in the context of the magnetic skyrmions. Okay, this S can be the skyrmion texture, but remarkably, these ideas of emergent fields already appear in Michael Berry's paper. Another way to think about this problem is to consider, instead of thinking about the continuum, which may be a bit abstract, you can think about particles, electrons hop on the lattice. And again, at every site, there's a large Zeeman field that forces electron spin to be aligned locally. And in this case, then, think about the hopping between adjacent sites. So when the two spins are aligned, let's call that hopping T. This is Baire hopping. But if the spins of electrons on adjacent sites are forced to be in different directions, then the effective hopping is reduced by this factor, which is the overlap between the two spin states. And so one thing we immediately see is that the magnitude of the hopping is now reduced by a factor that depends on the relative angle between the two spins, adjacent sites. Now, this reduction of the hopping amplitudes leads to a reduction of the bandwidth. Okay, in the lattice model with hopping T, if it's hopping T, we know that the dispersion is something like minus ZT cosine K times A. So at the band bottom at K equals 0 has energy minus ZT. But when the spins are varying from side to side, the reduction of the hopping then effectively reduces T. So the bandwidth is reduced and the band bottom goes up. So this increase of the band bottom is exactly the geometric potential that I mentioned earlier. That if you look at this, that after this unitary transformation, when we project a low energy subspace, you see that compared to the original Hamiltonian, there's an extra potential that's always positive. So the physical origin is that when the internal state of the particle is spatially varying, the hopping is being reduced. Okay, that leads to a potential effect. And the other thing is that if you have a particle hop around 3 adjacent sites, now it pick up a phase factor, which is a product between the 3 overlaps, 3 spin overlaps, and it's straightforward to show that this phase factor is exactly the solid angle spanned by the 3 spins. Okay, and this is exactly the Barry phase term. Okay, now for those curious, let me also advertise a recent work by my student Yugo Onishi and Nishaga. We showed that these 2 effects, the Barry phase effect is to leading order in H bar, the geometric potential is to quadratic order in H bar, but both of them are independent of the energy gap separating low and high energy space. One can carry out this expansion to even higher orders, and the next order is a correction of order H bar squared divided by mj. Okay, J is the energy gap between low and high energy space. And in this case, one finds that what happens is that depending on the momentum of the particle, it experiences a momentum-dependent correction. And this actually has a very nice interpretation in terms of the curved space, and it leads to an analog of gravitational effects. Again, in a material that moves, for electrons moving in free space. Okay? Yes?
In the previous slide, so with site binding on,
yeah,
is that a better approximation than the previous one?
The question is approximation to what? This is an excellent question. So the first thing is that these 2 formulations are equivalent. In other words, the lattice description will recover the continuum description in the limit of a low carrier density. If the density is very low, the wavelength of electron is very, very large. So then, this is the equivalent of saying that if I'm just zooming in to the planet bottom, then it will exactly recover the continuum description. And the reason that the continuum description is actually more universal is because real material is not going to be described by this simple model, which is basically s orbital electrons hopping with nearest neighbor, right? In the real material, the electrons are typically not in the s orbital, but there's SPD and f orbitals, and the hopping is not restricted to nearest neighbors, right? So the real material is very complex. But important thing is that if you go to low density, the electron's wavelength is much larger than atomic scale distance. Then these details does not matter anymore. So the continuum description is the universal description for systems at low density. Yeah, this is an excellent question. But the lattice model can give you a good intuition for understanding. Okay, so I'm going to focus now on a class of spin textures that are periodic. Okay, so these are, for example, in the magnetic skyrmion materials, there's usually a long wavelength spin modulation, and the spin texture then defines a mapping from the Brillouin zone, which is equivalent to a torus, to a Bloch sphere. Okay, and in this case, the emergent magnetic field is given by this quantity, which is sometimes called a spin chirality. It's non-zero when spins form a non-coplanar pattern. But if you look at the total flux through a unit cell, this quantity is actually topologically quantized. It's guaranteed to be equal to the integer winding number of this map from the torus into the Bloch sphere. Okay, and in particular, if you take a skyrmion pattern like this, okay, at the origin, spin is pointing out, far away, the spin is pointing down, and in between, the spin is rotating in the XY plane. If you take this kind of a skyrmion pattern, one can show that the topological invariant is 1, meaning that each skyrmion carries 1 emergent flux quantum. So then what this shows is basically you take a material with no external field, but it has a spatial varying spin texture. It really has an emergent magnetic field, and this emergent magnetic field can drive the analog of the Hall effect. And that's called the topological Hall effect. Has been observed in many systems, in many magnetic skyrmion systems. So then we ask the question, what about the quantum Hall effect? Right? can we find something like a quantum Hall or fractional quantum Hall effect in this skyrmion materials using emergent magnetic field. This is work with Nishaga Paul, student, and Yang Zhang, postdoc at that time. Now, just like the condition for quantum Hall effect requires a low density, long mean free path, here in the magnetic skyrmion materials, most of the magnetic skyrmion materials has a very large skyrmion period, and while the mean free path usually is shorter than that. So this is exactly the opposite to what we want. So in order to fix this, we conceived some sort of heterostructures. You take a semiconductor MOS2 in proximity with a magnetic 2D material, for example, chromium, bromium. By DFT calculation, our DFT calculation shows that there's a large exchange splitting on the order of 14 millielectron volt. So this exactly realized a situation of a particle with a parabolic dispersion coupled to a skyrmion texture. And if the skyrmion lattice constant is relatively short, the mean free path is long, then we can talk about the formation of bands, the analog of lambda levels in this setting. And our calculation shows that for various types of the skyrmion textures, the low-lying part of that energy spectrum very often shows flattron bands. Okay, in particular, as we sweep the magnetization of the system, there's a magic magnetization where the lowest band, lowest mini band is actually almost completely flat. So this led us to propose some kind of a semiconductor, a magnetic heterostructure in 2D materials, maybe a good platform to realize this. The training insulators and the fractional training insulators. And here, time resolution symmetry is broken by the spin ordering in the magnet. This has still not yet been experimentally achieved. But then, further taking this idea, if we want a spatial modulation of some kind of a texture, the best platform is moraine materials. Okay, so the 2D atomic thin materials, they show graphene and semiconductors. For example, you can stack them. You can create homo bilayers or twisted homo bilayers or hetero bilayers. Because of either the twist angle or the lattice mismatch, you can create a long wavelength periodic modulation. This is moraine, right? So what we want is some kind of a periodic modulation in the underlying Zeeman field. So can this be realized in moraine systems? So then we found this paper by Alan MacDonald considering twisted homobilayer TMD, transition metal dichromatin semiconductors. In this system, what got us interested that in this system, if you look at the holes, they have very simple parabolic dispersion, and because of large atomic spin momentum locking, the spin up electrons is exclusively in value k, spin down electrons is exclusively in value k prime. So these two values are far apart in momentum space. So to leading order, we can treat them as decoupled at the single particle level. So the full Hamiltonian then can be for spin up electrons, lives in a two-component space because there are two identical layers, top and bottom layer. One can view the layer degree of freedom as a pseudo-spin. Okay, and on each layer we have a parabolic dispersion k squared over 2m, and there's an underlying moraine potential on each layer, which is V1 and V2, and there's interlayer tunneling, which is now the off-diagonal elements. Okay, now what's interesting is that because these holes live in valley K, if you look at the interlayer tunneling, it's strongly spatially modulated. Okay, if you look at the moraine structure, there's a MM spot where the metal atom of the two layers are aligned, and this is where the interlayer tunneling is real and largest. But then there are other regions where the metal atom in one layer is aligned with the charging atom on the other layer. So then in order to tunnel from one metal atom in the one layer to the next layer, there are three symmetry-related paths. Right, this is gray dot illustrates the metal atom. Okay, each metal atom in one layer in the XM region tunnel with equal strength to three nearest neighbor metal atom on the other layer. But because the block wave function okay, of these of states near the K point carries this phase factor e to the I k dot r. It's rapidly varying on the atomic scale. So the Bloch wave function amplitude on the 3 metal atoms, they all have different phases, 120 degrees apart from each other. Because of that, the tunneling is destructive interference. There's destructive interference, so the tunneling amplitude completely vanishes in the XM and MX spot. Okay. So for this reason, if you look at this whole Hamiltonian, with both interlayer tunneling and intralayer potential, it forms exactly the same structure as the Skyrmion problem. Okay, that the potential difference between the two layers is like the Zeeman field in the z direction. The interlayer tunneling, which has both real and imaginary part, is the analog of the Zeeman field in the xy plane. And the interlayer tunneling has strong spatial dependence. It even vanishes at these particular spots. So if you look at the texture, it is topologically a Skyrmion texture. So this means that there should be one flux, emergent flux per Maury unit cell. Okay, but this is not the full story. Everything I've told you is for a spin-up electron that lives in valley K. Okay, this material itself is non-magnetic. Okay, nominally it's non-magnetic. So there's also a spin-down state, which is a time-reverse partner, and that lives in K prime valley. So the emergent magnetic field is equal and opposite for the two spins, for the two valleys. So as a whole, what we get is at the level of band structure, we get time reverse pairs of Chen bands with equal opposite Chen number. So the whole system behaves as a quantum spin Hall system, very well described by the K-Malé model, and that was the original motivation for this work. So we started ask question, can we turn this platform into a platform for quantum Hall effect, for quantum norms Hall effect? Okay, and fractional quantum norms Hall effect. And this relies on electron-electron interaction to spontaneously polarize electrons into one value. And this spontaneous spin polarization comes with a price of typically increasing the kinetic energy, because previously both values have low-lying states for spin-up, spin-down electrons to occupy. Suppose all electrons become spin polarized, it typically has to occupy higher energy states. So the competition really relies on the bandwidth. Whether interaction effect is strong enough, crucially relies on bandwidth. So with Chithup, Valentin, and Yang Zhang back in 2021, we look at the DFT calculations. We performed DFT calculations for twisted TMD, WST2, and from this DFT calculation, we extracted the continuum model parameters, and this allows us to reconstruct the bands across a whole range of twist angles. And here, I want to focus on the topmost valence band, lowest energy band for the holes, and across a wide range of twist angles, you see that the band has a non-zero Chen number. This is for a given spin sector, but the bandwidth varies. Okay, the bandwidth depends strongly on the twist angle, and it can become very flat at the small angles. Also, when we look at the barrier curvature of this Chen band, the barrier curvature can be very uniform at a certain magic angles. And this led us to conclude that in this material class, we can get a flat Chen band, time reverse pairs of flat Chen bands at a magic angle, and then they would be very much similar to lambda levels. It could be a platform for fractional quantum Hall effect without external field. And furthermore, Valentin Kreppel performed serious exandization studies. You take the system with Coulomb interaction and project into these lowest two subbands. And because the total spin SZ is a conserved quantum number, we can look at the energy spectrum for different spin sector. Here, the red dots is a spin fully polarized sector, and other colors represent different spin sectors. And you see that in a range of twist angles, the system is spontaneous spin polarized, meaning that Coulomb interaction drives electrons all into one value. And this occurs not only at integer filling 1, not only at 1/3, 2/3, but across a full range of filling factors. So here the color represents the spin gap, the energy cost of creating a spin flip. Okay, And so this itself led us to conclude that this system would become a ferromagnetic, spontaneous ferromagnet under reasonably wide range of conditions across a whole set of fitting factors. Moreover, if you look at, for example, 1/3 fitting, and then we have a situation of a fractional fitting of a lambda level electron band, this is then should give us a fractional training filter, and indeed, here our excitation spectrum shows a 3-fold degeneracy, very much like a lambda level case. Yes?
Well, in this diagram, where is it filling exactly?
It's the y-axis. Sorry, the y-axis is a fitting factor. One is integer fitting, and this is half fitting, and 1/3 is here. This is 0.2.
But we're sourced because experimentally the make the fractal board comment for itself at equal size.
This calculation is for twist WSC2.
Oh,
yeah, but the physics is really similar. Yeah, and also I want to mention that there's another work by Kai Sun and Shizhen Lin that look at a specific 1/3 fitting factor. Their calculation is for twisted MOT2.
We think that I have to doctor the rather young and today.
Which aspect of the?
Yes, yes. Had some fun to keep thing that get back to it.
Yes.
And the next thing,
2/3 is larger. Yes. Yes. Yeah, I think it could be. So what actually this is a good question. So, unlike the true magnetic skyrmion system, right? In the magnetic skyrmion system, time reversal braking is provided by the almost classical like background spins, right? That they enter the Hamiltonian for electrons as a classical Zeeman field. Here, the energy scale for spin ordering and the energy scale for quantum Hall effect, fractional quantum Hall effect, is one and the same. It's all driven by the Coulomb interactions. There's no separate spin degree of freedom. There's no localized moment. All the electrons spontaneously, Coulomb interaction does two things at once. It drives spontaneous spin polarization, ferromagnetism, and this occurs, we showed that it occurs on a wide range of fitting factors, not tied to any particular fitting. But then, at special fitting factors, it drives fractional quantum Hall effect. Yeah, because two things occur at once, all through the same Coulomb interaction. Okay, so I, in fact, this work was completed in the summer of 2022, and the first time I gave this talk is actually here in the Tallahassee Winter School in January 2023. And at that time, the UW group, Xiaodong group, has been working on twisted MOT2 for a while. Initially, they were focusing on detecting ferromagnetism, which is the prerequisite for any quantum Hall physics, fractional quantum Hall physics, zero field. And this is the magnetic split dichroism, which basically detects ferromagnetism signal. And you see indeed that in twisted MOT2, this occurs not just at a fitting factor 1, but it extends over a range of fitting factors. Okay, and we started collaborating, in January 2023, the experiments are still ongoing. But then half a year later, the Xiaodong's group reported the beautiful evidence of this fractional quantum Hall effect. And this is the Hall conductors, Rxy and Rxx as a function fitting factor, all done at the zero magnetic field. And you see these plateaus, 2/3 and 3/5, etc. Okay, and this was also following optical signatures, which I'll talk about in a minute. Okay, and then when the range is paused, my colleague shortly afterwards in the same year, Long Zhu's group at MIT with Zheng Guang, they discovered remarkably this fractional quantum Hall effect also in rhombohedrographing HBN heterostructure. And in this system, it shows many more fitting factors. And this was really a pleasant surprise because this fractional quantum Hall in this system was not predicted. Okay, now one thing I want to highlight is that in both MOT2 and the rhombohedral graphene, okay, we see that the fractional quantum loss Hall effect occurs at filling factor P over 2P plus minus 1. This is the chain sequence filling factors. And the Hall conductivity in units of E squared of H is equal to the band filling factor. Okay, this suggests immediately that there has to be an underlying similarity between the Chen band in the system and the lowest amount levels. Okay, in the complete general setup, there's no reason that the Hall conductivity has to be equal to the band filling factor. We are not talking about the continuum space with Galilean invariance. We are talking about a lattice system that's broken Galilean invariance, and the fact that still the sigma xy is equal to the band filling factor immediately suggests there's an underlying similarity. Okay, so now I'm going to explore this similarity. So because this sequence is well understood as composite fermions in the lambda level setting, let's see whether it also applies in just KMDs. Very quickly, I'll just show you that our exantization calculation for the end spectrum at 2/3 filling and 3/5 filling, right, near the magic angle, which in this case, twisted MOT2, we found to be around 2 degrees. You see that the end spectrum is very similar to that of the lambda level system, right? All the low-lying states and the momentum sectors, they all match. Moreover, when we look at the charge gap in the system as a function of the filling factor, we see that the charge gap vanishes at 1/2 filling, and it grows almost linearly away from it. Again, this is similar to lambda level setting systems. Now we know that the chain sequence of the fractional quantum pulses terminates at 1/2 filling, which is a gapless compressible from liquid states. So this led us to study also the 1/2 filling in this system. And again, near the magic angle and the spectrum of twisted MOT2 and the lambda level is very similar. Now, one question that we are intrigued is, what should be the value of sigma xy at half filling? So in the quantum Hall setting, even though the composite from liquid state is gapless, there's no true quantization, sigma xy is very much 1/2 E squared of H. And again, one can understand that because of Galilean invariance. But in this system, in just MOT2, we have an underlying Morley lattice, translation symmetry is broken. So what should determine the value of sigma xy at half filling? Okay, so with Adi Stern, we studied this problem. Now, because the composite fermion state is obtained by flux attachment, attaching two fluxed electron to convert it to a composite fermion, there's a general relation between the resistivity, electron resistivity, in terms of the resistivity of the fractional particles in terms of the partons. This is sometimes Ioffe-Larkin rule. The rule says that the resistivity add up. Okay, if you want to view an electron as a composite of some fractionalized parts, each part has its own resistivity. Then the resistive tensor of the constituents add up to give you the resistivity of the underlying electron. Okay, so roughly speaking, the one that is most resisted becomes the bottleneck for the electron. Okay, now for the flux, when you attach flux, which are really vortices, vortices contribute. These two vortices contribute to a Hall resistivity of 2H over E squared to the full resistivity tensor. This is completely off diagonal. Epsilon ij is a fully antisymmetric tensor, 2x2 matrix. And then the question is, what about the composite fermion? Okay, the conductivity. Now, in general, this composite fermion conductivity has both diagonal part, sigma x and sigma xy. Okay. Now, the value of sigma x and sigma xy depends on details. For example, sigma x certainly depends on the level of disorder in the system, and sigma xy may depend on the Barrett curvature of the underlying Chen band. But regardless of details, as long as the composite fermion conductivity is predominantly dominated by longitudinal part, if the diagonal components is much larger than the off-diagonal component, okay, then the true electrical resistivity is dominated by the flux, by the vortex part, and it will immediately give us 2H over E squared resistivity that is mostly in the Hall channel. Okay, does that make sense? Because composite fermion, on average, at half filling sees no magnetic field. So as long as the disorder is low, then the longitudinal conductivity dominates over the Hall conductivity for composite fermions. And then the sum rule tells us the electrical resistivity is dominantly in the Hall channel, and its value should be close to 2h over e squared. And this explains the transport observation that you see that even though this RXY away from these plateaus can have all kinds of interesting behavior, near 1/2, its value is still close to 2h over e squared. Now, another important question is about the Fermi surface of composite fermions. In the case of gallium arsenic community, one way to probe the Fermi surface composite fermions is to through this commensurability oscillations. So the idea that even though at 1/2 filling, composite fermion sees zero flux, if you move slightly away from half filling, composite fermion will see a small magnetic field, and which will drive cyclotron motion. If the cyclotron motion is commensurate with some external periodic structure, okay, with the cyclotron radius is commensurate with some external structure, then the resistivity will show oscillations. Excuse me, yeah. So this is the data from Mansfield-Shagan's group, and you can see that there's a whole sequence of fractional quantum Hall states, the Jane sequence. But if you look very close to 1/2 filling, okay, there are additional wiggles, and this is a blow up, and the filling factor associated with resistive wiggles can all be understood by this resonance condition when the cyclotron radius is equal to some integer multiple of the external periodic structure. Okay. Now, for us, we don't need any external periodic structure. The system itself is a Moiré material. It has an underlying Moiré potential, right? So this led us to propose that there should be an intrinsic commensurability oscillation, and keeping magnetic field at 0, if we just change electron density, at half filling, composite fermion sees 0 net flux, but away from half filling, it will experience a flux, which is given by 2 times the deviation from 1/2. And when this magnetic flux gives rise to a resonance between the composite fermion cyclotron orbits with the Moiré lattice, we would expect an oscillation, right? Now the question is, what determines this of this resonance condition? Okay, so in the 1D system, this was understood a while ago, but for this general problem, we have now a 2-dimensional periodic potential with a symmetry of a triangle lattice. And what is the general condition for geometric resonance for particles in the magnetic field and the periodic potential? And this was worked out by Nishaga Paul, collaboration with Philip Crowley and Tristan Devico. What these guys found is that one can understand this whole geometric resonance in the following way. Suppose we take the limit of when the periodic potential is much smaller than the cyclotron energy, then the effect of the periodic potential can be understood by projecting the potential into the nth Lambda level, okay? And for example, if you have a potential, which is sum of cosine q times r, and q is the reciprocal vector, this is a bare potential, but when the v is small compared to cyclotron energy, one can project this v into the Lambda level subspace, and this derives the effective Hamiltonian. Basically, the position operator r should be replaced by the cyclotron guiding center operator, and because of all the underlying Lambda orbital wave functions, this potential strength is renormalized, and in particular, pick up this form factor that is given by the Laguerre polynomial, and the argument of this depends on the reciprocal lattice vector q of the periodic structure. It depends on the magnetic length. Okay. Now the interesting thing is that this polynomial has zeros. So what this means is that if you look at the any spectrum Lambda level, right, in a high field, for example, you can expect without the periodic potential, you just expect equally spaced Lambda levels. But with a weak periodic potential, the generally lambda level will be broadened, but at the special magnetic field, the broadening vanishes. So we call this magic zeros. And this is exactly what gives rise to a geometric resonance. In other words, at a certain magnetic field, the lambda level broadening vanishes. So one expect correspondingly a oscillation in resistance. And in particular, when the cyclone energy is much smaller than the Fermi energy, when we are in the weak field limit corresponding to the large lambda level index, one can express all these lambda level index at the Fermi level. One can express it in terms of magnetic length and the Fermi wave vector. And one can also express Kf and Lb squared in terms of cyclone resonance. And then this magic zero condition will exactly give us the following classical expression, which says Kf times the reciprocal lattice vector Q times magnetic length should be equal to some multiple of some integers, set of integers, okay? And, if you look at the expression for 1D periodic structure, it recovers the previous known geometric resonance condition, but now for 2D triangle lattice, it gives us this condition with a different prefactor. And because in this system, the Kf, the composite fermion wave vector Kf, which is set by density, and because we are at half filling of a band, this density is exactly related to the geometric area of the Morat unit cell. So everything in the end cancels out. All the length scale cancels out. So what we expect is that there will be a set of oscillations, okay, intrinsic geometric oscillations. And if we express the resistance extrema, the filling factor at which it occurs, then the 1 over delta nu, which delta nu is a deviation from half filling, it should be equally spaced. Okay, so there's an oscillation that's periodic in 1 over delta nu, and this should be independent of the twist angle, independent of the unit cell area, and it should have this spacing that is just purely given by this number, 0.43. Okay, that's still a prediction. Okay, can I just use 2 minutes to wrap up? Yeah. All right. So, so let me just summarize. So I've described the quantum Hall effect that's driven by real magnetic field, and one can think about the phase diagram in the density and magnetic field. The quantum Hall states appears along these lines, okay, with quantized coefficient. This is set by the Strader formula. So if you move along these lines, you're at a fixed filling factor. This is nu equal 1 and nu equal 2/3. And these quantum Hall states, fractional quantum Hall states, only appear when the magnetic field is sufficiently large. So that's why the onset at some finite. On the other hand, in twisted MOT2, right, there's no even at zero external field. There's an emergent magnetic field that drives the system into these quantum Hall and fractional quantum Hall states from emergent field. But then if you further apply a magnetic field, okay, you find that the density at which it occurs will shift. And it's very similar to the quantum Hall case, but now everything goes down to zero field, okay? And this slope is actually determined by Strader formula to be exactly related to the quantized sigma xy. So this is actually the initial evidence of fractional quantum Hall effect, not from transport, but from optics, okay? So by tracking the incompressible gaps as a function of density and magnetic field, we suggested that this could be a way to detect fractional quantum Hall. Okay, now back to the question. Why do we need a 200 Tesla real field? Okay, this is my last slide. So to summarize, right? If I now compare these two cases for fractional quantum Hall or fractional training insulators, a zero field, we already have quantized states, and the density of these states will evolve with magnetic field. Okay, now the reason that it occurs already at zero field is because even though the external field is zero, there is a large emergent magnetic field which corresponds to 1 flux quanta per Morat unit cell, right? So one should actually compare this side and this side with an offset. Okay, and in particular for a twist angle of 3.7 degree twisted MOT2, the emergent flux is about 200 Tesla. Okay, so now imagine we take twisted MOT2 and we suppose we can apply an opposite field of 200 Tesla. Then it will cancel the emergent magnetic field. What this will do then is to restore composite fermions that are spontaneous form at zero field, convert them back into nearly free electrons. So then we would expect we can kill the fractional quantum non-solid state and restore a system with nearly vanishing RXY. Suppose electrons can be kept in the same valley, then the prediction is that zero field, you see a quantized RXY, but if you apply an opposite field around 200 Tesla, then it should go to zero, RXY to go to zero. So that's why we need a 200 Tesla field. Okay, thank you.